Hello, my name is Dennis Chavez Romero,
Hey, my name is Samad Shah.
and this project will cover the dynamic fiducial marker tracking of a serial manipulator. The objective of this project aimed to expand upon the available options to perform object tracking in the realm of cinematography. Our motivation stemmed from the need to provide better alternatives to do 3D visual tracking. Currently, the conventional methods that rely on robot-mounted cameras to pan across shots while dynamically tracking a target usually requires a lot of heavy image processing, and it often involves steps like camera calibration, color selection, noise reduction, roundness measurement, generation of dynamic search windows, and position estimation. And essentially, all of this can lead to multiple sources of error that can decrease the quality of the tracking. So an alternative to do regular object tracking while masking an image would be to instead track a fiducial marker. In our case, it would be an April tag. So we chose to go with the Panda ARM because it offers a wide array of open source applications. And if you're going to be running this in a physical Panda ARM, then it usually comes with easy to follow steps to get it integrated in ROS. So the ROS packages that we used are April tag ROS, ROS control, and TF. So the way this works is that we have a spawn model of the Panda ARM in Gazebo. So the Panda ARM controller command topic communicates with Gazebo, which then updates the Panda ARM joint states topic, which then gets used by the robot state publisher, which then updates our TF node. So our forward kinematics then gets the end effector pose by communicating with the Panda ARM and getting the current joint values from the model, and then that topic gets used by the inverse kinematics to calculate the desired joint values based on our current end effector pose that we use as our current cue whenever we perform the Newton-Raphson numerical approach for inverse kinematics. So then we have an April Tech continuous node, which uses data from our camera info and camera topic nodes, which publish data about our camera parameters as well as our camera video feed. And then that gets sent and used by TF. So this camera or this April Tag continuous node publishes a series of tag detections into our tag detections topic, which then gets used by our tag to world transform publisher to publish a tag detection post stamp message in the world frame. So the output of that gets broadcasted over our tag and world topic, which then gets used by our desired pose publisher node, and that actually carries out the calculations required to get a point in space that represents the April tag into a pose that our arm is able to reach, and the output of that gets published to our desired point topic, which then gets used by our position tracker. So then our position tracker makes a service call to our inverse kinematics node, and the output of that service call gets used to make another service call to our trajectory controller server, which then actually drives the arms joints to our desired joint values that have been calculated by our inverse kinematics. And that happens continuously as the April tag continues to move in space and gets picked up by the camera. So the main experiments that we performed to verify the correctness of our solution were to first just move the April tag around and to random points in the camera's field of view and see how well the tracking performed in that scenario. And after that, we actually drew out a heart-shaped trajectory in 3D space with the April tag and observed how well the end effector was able to keep up with the April tag while it performed the trajectory and was getting picked up by the camera.
Let's look into the results now. So in the previous few slides, we saw that we moved the April tag in a heart-shaped trajectory and we could observe it in real time on our Vision Gazebo. So what I did is I decided to take in the values of the joint position, joint velocity, and joint efforts from the joint state topic and plot these values on MATLAB. So first you can see that I plotted the position of end effector in space, and we can see that it has a component in the x-axis as well. So the heart also has a lateral movement while plotting it, and we were able to successfully make a heart. We can see not the best one, I would say, but we are close. So I decided to split these parts into A to B, B to C, C to D, and D to E, which will help us understand the graphs better. So when we look at the joint position versus time graph, we see that joints 5, 6, 7 hardly contribute anything to the trajectory, and that can be implied from how the trajectory is. And we mainly need horizontal motion, and this basically is given by the joints 1 and 3, which are rotating the bot. So they help us achieve the motion from B to C and C to D. And joints 4 and 2 are the ones that help us achieve that vertical and lateral motion of the bot, and that is why they keep rising and falling down based on where they are in space. And let's look into now the joint velocities graph. In the joint velocities graph, we see that joints 1 and 3 have major changes when it reaches the middle of the heart, and this is because the main horizontal motion that happens quickly is from B to C and C to D, and that is why the joints 1 and 3, that is the moment when they change slightly in the joint positions graph, if you see, and that is why there's a huge velocity difference that we need to create this motion, and that is why they have such high velocities. And joints 2 and 4 follow a similar trend. They keep going up and down based on where they are. Now let's look into the joint efforts graph, and we see similar trends that joint 2 and joint 4 follow the same up and down motion based on where they are, and joints 1 and 3 need huge torques, and this is because they are basically rotating and carrying the entire mass of the robot with them, and that is why the torque requirements are so high. Another thing that we observe is that these graphs are not very smooth, and this is because we did not consider the velocity and acceleration of the April tag, and because of that we passed in 0 values for the velocities at each waypoint. So what happens is the controller tries to bring the joints to 0 velocity, but immediately it gets a new point, and that is why it's not able to achieve that 0 velocity. So you see that it keeps spiking up and down because of that, and this is something that we need to improve in our further goals. So looking into the conclusion, we were able to actually successfully move the April tag in real time with minimal error, and the path was smooth. Further improvements can actually be made in making these velocity and acceleration variations smoother, and this can be done by tracking the April tag's velocity and acceleration and then passing it into the quintic polynomial, and then performing a dynamic model that should be developed by ourselves, and also design a controller over it. And this could be our next goal for RBE 502, the control subject. So that's pretty much it. Thank you guys for watching. Have a great day.